Okay, let's move on to application of sparse representation. Here we discuss applications of sparse representation or sparse optimization to spline curve fitting and discrete time hands-off control. So let's start with splines. We here consider the problem of curve fitting. We are given two-dimensional noisy data D. Then we find a function which is not necessarily a polynomial y of t that the best fit to the endpoint data, as shown in this picture. We here consider spline in particular. The spline curve fitting problem is described as follows. Find a smooth function y over 0t with the second derivative y2 dot in L2 0t that minimizes this cost function. The first term is for the fidelity of curve fitting to the data, and the second term here is for the smoothness of the curve. This is an infinite dimensional problem since we seek a function in a functional space, not a finite number of parameters. This can be reduced to a finite dimensional optimization problem by using techniques in Hilbert space theory. I will explain this in more detail. The problem is given by this. By the change of variable, this can be described as an optimal control problem as follows. Let x1, x2, and u as follows. Then the problem can be rewritten as this. Namely, minimize this cost function subject to these constraints described by differential equations. Now, we consider more general problem described as this. We minimize the same cost function under the constraints of state space equation here and output equation and initial condition. Let's consider this problem. First, we define a two-variable function Lt tau defined by this, where this is the impulse response of the state space equation. Also, we define phi I of t equal to Ltti from the data. Then, from the solution of the state space equation, we have y of ti, the sampled data of the function y, is given by the inner product of phi I and u in L2, which is described by this integral. Now, the problem becomes this unconstrained optimization problem. We further rewrite the problem as this. The constrained problem where Zi here is defined by this. From this, we define a new Hilbert space H. The product of L20T and Rm with inner product defined by this. Namely, the inner product is the sum of the inner product in Rm and the inner product of L2. Then the cost function becomes this simple expression. The squared norm in H of R minus P, where R is defined by UZ with Z is Z1 to Zm, and P is defined by 0y, and y is a vector of y1 to ym. Then let's consider the constraint. Let us define a closed linear subspace M of H by this. From this, the constraint Zi is equal to the inner product of phi I u becomes P 0y in M. Finally, the optimization problem is now rewritten as this. By the definition of projection, the minimizer is given by the projection of P in H onto the closed linear subspace M in H. That is, the minimizer R asterisk is the projection of P onto M. This picture illustrates the projection. We have a vector P in H and a closed linear subspace M here. Then the minimizer R asterisk here is the orthogonal projection of P onto this linear subspace. Then let M pop denote the orthogonal complement of M in H. That is, M pop is defined by this. Then, from the projection theorem, the minimizer R asterisk is in the set of the intersection of M pop plus P and M. This picture shows the projection theorem. We have P here and the closed linear subspace M here. M pop is another linear subspace of H, and the projection of P onto M is the intersection of M pop plus P and M. Here, M pop plus P is a parallel shift of M pop by the vector P. Let us characterize the set M pop plus P and M. First, we look into M pop plus P. Take V W in M pop arbitrarily. Then for any uz in M, we have this equation, namely the inner product of these vectors is 0 by definition, and the inner product is equal to the sum of the inner product of vectors and inner product of L2 functions. Then, since Z here is in M, so by the definition of M, Z is described by the inner product of phi I and U. So we have this expression for the inner product in Rm, and also the inner product of two functions in L2 is described by this. And finally, by using the linearity of the inner product, we have this expression. Now, we have the equation of this. And this U is chosen arbitrarily, so by this equation, we have this, that is, this function should be 0. By this equation, we have the expression of function b like this, since lambda here is positive. From the expression of function b here, the subspace MPUP can be represented by this. I just inserted this expression into the definition of MPUP. Then adding p equal to 0y to this, we have MPUP plus p is equal to this set. Remember that the optimal solution R asterisk, denoted by U asterisk and Z asterisk, is in the intersection of these sets. First, since R asterisk, the optimizer, is in the set M, we have this relation for each I, 1, 2, and M from the definition of M. Next, since the optimizer R asterisk is also in MPUP plus P, we have this equation because MPUP plus P was given by this. Then inserting the two equations into the first equation, we have this equation. Then defining the Graham matrix here using the inner products, we have a simple expression of this equation as this. And since the parameter lambda is positive, we finally obtain the vector w given by this. Note that the vector w is the coefficient vector of the optimal solution used asterisk of this. Therefore, the optimal solution U asterisk is given by this. The linear combination of phi I with coefficient alpha I, which is given by this formula. Finally, the optimal curve is given by this formula, double integration of u, since u was the second derivative of y. Okay, now let's consider sparse representation. We have seen that the optimal solution is given by the linear combination of phi i's with coefficients alpha I given by this equation. Let's consider sparse representation of this. That is, we find sparse coefficient vector z of the linear combination of phi i's. From the expression of u, the linear combination of phi I, we have this equation. Namely, inserting u into this, then we obtain this. And by using the linearity of the inner product, we have this expression. Hence, the first term in the cost function becomes this, inserting this formula into this. Here, G, here is the Graham matrix. Also, we have this equation for the second term of the cost function. Here we also use the Gram matrix. Therefore, the cost function becomes this. Now we formulate the sparse representation of z by adding the L1 term here with a positive parameter rho. This cost function is a sum of a quadratic function and L1 norm. And this can be solved by Pfister algorithm as we studied before. Now we discuss discrete time hands of control. Let's consider a discrete time linear system given by this state space equation. Then we here consider the following control problem. Assume that the initial state x0 is xi is given by state observation. Then find a control sequence u0, u1, and un-1 such that the control drives the state x of k from x0 equal xi to the origin. That is, x of n is 0. First, let us consider the feasibility of the control problem. From the state equation here, we have the solution described by this equation, where the matrix phi is defined by this, and the vector u is the control sequence, including u0, u1, and un-1. Then we define the set of feasible solutions, or the feasible set un xi by this. Now we check if this set is empty or not. It is easily proved from an elementary control theory that if n is greater than or equal to d, where n is the horizon length and d is the dimension of the state space, and the plant is controllable, then the feasible set un xi is non-empty for any initial state xi in Rd. From now on, we assume these properties hold, and the feasible set is non-empty. We then consider optimal control described by this, where Ju is the cost function with stage cost L. If L is a quadratic function of x and u like this, then the problem is called the LQ, linear quadratic control. If L is the L0 norm of the control vector u, then this problem is called maximum hands-off control or sparse control. As we discussed before, this is a difficult problem. And we relax this to L1 optimal control, which is also known as minimum full control. Here we consider the L1 optimal control with this. The optimal control problem is described as this. This is exactly the same as the L1 optimization we studied before, so this can be solved by Douglas-Rashford splitting algorithm or ADMM. The control is finite horizon and hence feed-forward control. Then we can easily extend the finite horizon control to feedback control using model predictive control MPC formulation. It is important to prove the stability of the feedback control system. For this, Lyapunov stability is guaranteed if A is non-singular and asymptotic stability if A and A minus identity are non-singular. Also, these properties are proved assuming that the L1 optimal solution is exactly computed, or we can do infinitely many iterations in ADMM in the feedback loop. This is not useful for real systems, but we can prove that a single iteration of ADMM in the model predictive control also guarantees input to state stability, which was proved in this article. If you are interested in this article, which is not published yet, I can share this paper with you. Now let's summarize this section. Spline curve fitting is an infinite-dimensional optimization problem. By Hilbert space theory and the projection theorem, the optimization is reduced to a finite-dimensional problem, namely a quadratic optimization problem. Then we can easily adapt sparse representation for spline curve fitting. Then we discussed maximum hands-off control for discrete time systems. Finite horizon L1 optimal control becomes an L1 optimization problem. Feedback control by MPC is also considered, and stability results are proved.